Welcome to this first recorded video for the Part A notebook in the Module 4 on some useful computational applications where you'll use the knowledge you've gained in the first three modules for this course. We're going to go ahead and import NumPy as MP and PyPlot for Matplotlib as PLT as is usual at the start of each notebook. Now, in this module, we will pull together material across our first three modules to solve some practical problems. You may find it useful at times to review the notebooks in those previous modules, or simply open some of them to have their contents available to review as necessary. While there are a seemingly endless number of practical problems we can attempt to solve with what we have learned so far, we focus on three within this module that are fairly ubiquitous in the computational and data sciences. One is root finding, which is the content of this module. The Part B lecture notebook will cover numerical integration, and optimization applications will be pursued in the homework notebook associated with this module after you've gone through the lecture notebooks of Part A and Part B. So we form some optimization problems, and they require you to use root finding and numerical integration at various points within that optimization assignment. So a note about calculus concepts and interactive visualizations before we start, meaning the use of widgets, which we introduced at the end of the third module for this course. These topics are commonly studied as applications of calculus concepts, so meaning all of these concepts right here, root finding, numerical integration, optimization. However, while we make passing reference to certain calculus concepts, you do not need to actually know calculus to follow the narratives that we're providing. This is not to say, of course, that you should not seek to master calculus at some point. Our focus is on the big picture ideas, and we use interactive graphics, meaning widgets, to help explore these ideas. So at the end of Module 3, you might recall that we introduced the concept of derivatives, and we showed how to numerically compute it with a Python module. And similarly here, a lot of the coding and calculus concepts are kind of presented very completely for you, but we're going to focus more on using these snippets of code and ideas to solve problems, and then to just manipulate and start to develop an intuitive understanding. So some learning objectives for this notebook. First, we want to understand what a root finding problem means and how they arise in practice. We want to apply different types of root finding algorithms to various functions, written as Lambda Python functions, which you've seen in a previous lecture. We will create code that implements root finding algorithms of different types, and we will create annotations and interactive widgets to enhance visualizations of data. There are some additional learning objectives that happen in place. As you work through this notebook, you'll start to see and learn some other things. So some of these that you will come across are the comparison and analysis of different algorithms developed for solving the same generic problem. You'll see or be asked to use this comparison to describe how you might choose the right algorithm for solving a specific problem. You will create a module that encodes various algorithms and a wrapper function that automatically chooses which algorithm to apply based on the inputs. Now, some of this is done in this notebook, while other parts, for instance, this last one, is left for the homework. So the notebook contents, this recorded video for the lecture will just go through the introduction of the concepts, and then I'll have separate videos that go over the bracketing methods and the iterative methods separately so that each video is kept at a manageable length. Now, so this video will be here, and I imagine you're already running it, so you know that. This is our introduction to concepts. What does root finding actually mean? Basically, it just means that if you're given a function in the familiar form f of x, a root of that function is some input where x is equal to c such that at that input f of c is equal to 0. Basically, roots of a function are the inputs that make the output equal to 0. That is not that complicated of a concept. Lambda functions are going to provide many simple examples. So we mentioned these only briefly in the Part B lecture notebook for the third module in the context of list comprehensions. So you may want to review that briefly for some more context. A lambda function is very useful in the context of this notebook, so we dive into them a bit more here. What is a lambda function? Well, I provide links for you to read that I really suggest that you spend 10, 15 minutes exploring that material. But the main takeaways for the purposes of this recorded video, what we're just going to get into, and again, I do want to highly encourage you to use all the links and resources I'm providing and spend some time reading that for yourself and developing your own examples. But the main takeaway is that if you have a simple type of what we call an anonymous function that you just need for a short period of time in your code, then a Lambda function is probably right for you. It is certainly not necessary to use these, but they are useful. A generic use syntax that we care about would look something like this. We would perhaps just say, well, I just want to call some function f just for quick reference. And so I'm going to say f is equal to lambda, and then I'll provide the arguments to the function, and then a colon, and then the expression that evaluates the arguments, that returns an output. So we'll run the code cells below to see an example of a lambda function in the context of plotting the roots of a polynomial, i.e. where the polynomial is equal to 0. Now you should pay attention to how we use these types of functions in this lecture. Basically, we just keep overriding f because we don't really care what f is or we don't care that it stays the same throughout the whole lecture. We're just wanting to have a function f that we can just evaluate f of x, and we want to change that f whenever we want to. And so lambda functions are a great simple way to do that. And there's also times where you don't even need to make f equal to anything. You can just, if you're using the function in place, you actually only need this part. And that is something that you saw in list comprehensions. So let's just go ahead and run this code. So this has now defined a function f such that f of x is equal to the third order polynomial. Remember, to raise a number, a variable to a power, you use 2 asterisks. So this is x to the third minus x minus 2. So now I have that function f defined. And then here is a lot of code that all it's doing is plotting. So this is a crash course in using plots to tell a story in really 2 easy steps. Step 1, plot your stuff. So the first thing I do is I create a figure, and I'm just saying a figure of a certain size. Now I use the linspace command we've seen before to create 100 uniformly spaced points between -1 and 2. I then plot the function values versus the x values. So remember, here's the x values and here's what we call the y values, f of x. So x and f of x. And I'll just go ahead and add some spaces, as is good coding practice, to some of these terms. There we go. It makes it a little more easy to read. So that's just going to plot the function as a blue curve with a line width that's slightly thicker than the default, which is usually of 1. Now I will add some axes to the plots. That will be done using the AXV line, and I'm putting that at 0 because that's where the typical y-axis is plotted in most plots. Similarly, I'll use a horizontal line for the axis, and I will plot that at 0 where the typical x-axis is. So I use a dotted line style and black lines, and then I know for this polynomial about where the root is. The c value that makes f of x approximately 0, f of c approximately 0, is about 1.521. So I'm just going to go ahead again, and this will all be fixed for you and what's submitted to you. So I'll have some more spaces there for readability. And now all that does is plot this function, and then it plots this point as a scatter plot on the same plot. And I'm using a red marker. This is a size command for that marker, and I'm making it a square. That's all I'm doing. So this is nothing fancy. Now step 2 is to make things a little fancy. I will annotate and add informational text to explain your stuff from step 1. So step 1 is just plot your basic stuff. Plot the curve that you're working with. Plot something related to a value that you care about on that curve. In this case, it's a root. And now I'm just going to create a string where I'm formatting certain numbers into text, and I'm then going to plot that as the title, and I'm setting what the title size is. Now I do something even fancier. I create an annotation. I'm annotating the plot. And the way I'm doing that is with a box that contains text, that is the annotation, and an arrow. Now I have a dictionary, 2 dictionaries actually, one that defines various properties of the bounding box. I want the box style to be round. I want the face color of it to be blue. I want color to be red. What might that be? We'll see. The alpha is 0.5. This is a value that you choose between 0 and 1 that determines the transparency. And then the line width, this is for the bounding box, right? So this is for how wide I want the boundary of the box to be. That will be line width too. Now my arrow, I specify an arrow style. You can read more about what these properties are by Googling and looking up the information involving the annotate function within PyPlot. But I'm making that arrow black. I'm setting the transparency on it. And then I'm also making it width 2. And then with those dictionaries, they get passed as right in here when I use annotate. I say, what should the bounding box dictionary be? Well, the variable that I've made this dictionary that I called the same thing, bbox. And what should the arrow properties be? This is the keyword there. Well, I'm going to make them also this dictionary, of course, that has the same name. And then the annotation is approximate root. I'm specifying the font size of that text. I'm specifying a coordinate with relationship of where the arrow should be pointing. And I'm saying where the text should be located. And you're noticing I'm offsetting it from this value. And then I'm saying the color should be white. So let's go ahead and plot this and then connect and make sense of all of these plot commands. So here's your plot. Here's the curve. You notice the axes as the dotted lines. And all of that was done here, along with that red square that indicates the approximate root. That was all of this right here. The title was determined by these two commands. And then here is where the location of my box is that contains my annotation of approximate root. You see the red color that I set was setting the boundary box color as red. The alpha transparency can be adjusted. So if I made this, let's say, watch what happens if I make this 1. Look how much darker it is. I like it generally around 0.5 to 0.25. Somewhere in that range is usually, I think, a nicer kind of lighter color to make the text pop out a little bit more from it. So the face color of it being blue, the boundary of it being red, it just makes it kind of pop out, and it's complementary colors I chose to the curve. You can do your own style. This is just what I chose. And then here you see the location of my text was at, remember the C value is here, 1.521, I believe is its approximation. And then I subtracted 1.25 from that, and that positioned this text box over here on the x-axis. That's why it's offset to the left of that point. And then I used 1 to offset the vertical placement of the text. And then all this is saying is this is the XY value. That's where the arrow should be pointing to, right? So it points from this text box to the point where the root is. And you see that's where the arrow is pointing. And then the white is the color of the text. You can make it black if you want. I think the white pops a little bit better against the black. Certainly, if you wanted to make your face color here black, and then a white text would definitely be preferred, I think, as that shows up quite nicely. So you can play around with this however you want. I highly encourage you to get a sense of what each of these pieces does. But once you see it, it does look like a lot of options, but they become pretty self-explanatory. You have this as a template to play with and just see which style you like. I leave it up to you to determine a style you like, and then you should just be consistent throughout. Although you don't have to be. It's just generally recommended to not be too distracting by changing the style of your presentation constantly for somebody that you're trying to explain things to. So that's what a root is. It's where the function 0, and here's how to plot and create an annotated plot, kind of a very fancy plot that's illustrating the root of a function. Of course, I haven't yet shown how I knew that was a root or how to approximate it. And I haven't really said why we should care about roots. So let's talk about these things before we finish this first video lecture. So why should we care about roots? Well, there's not exactly anything particularly important about a general function being 0. However, in a lot of problems, there are reasons to find where a function or something related to a function you're studying is equal to 0. For instance, if we launch two projectiles with two height functions, let's say denoted by h1 and h2 as a function of time, and this was telling you where the values were, you might want to know when these are at the same height, because that might be related to where, at what time, the objects collide. So this is an important question that arises, for instance, in missile defense systems, satellite monitoring, and even autonomous vehicle guidance systems, meaning self-driving cars. Not that it would be heights, but it could be locations on a street. So if we define f of t to be equal to h1 of t minus h2 of t, then we are interested in knowing whether or not f of t is equal to 0, and where, if it is ever equal to 0, at what values of t. What are the roots? There's some additional options here. I'm not going to read all these to you, but there's plenty of them. And what you might recall also from when we discussed the computational module involving derivatives in the third module for this class, that where the derivative of a function is equal to 0 is often where the function is has its maximum or minimum values. So they do come up quite frequently, and then you have to ask, how do you actually solve these problems? Well, it turns out there's a lot of algorithms that attempt to approximate the roots of a function, and I provide a wiki link here that you might find interesting to review, and I do encourage you to read a little bit more about root finding algorithms. But there are a few key points to walk away from, to take away from, that article. Most of these algorithms are iterative, meaning we need to write loops to implement them. So we will be using what we've learned in the third module in this class in terms of writing loops. Another key point is that some algorithms are very easy to implement. Some are considerably more difficult. Now, something to keep in mind is that generally, the easier something is to implement in code, the more restrictive the conditions are under which we expect it to produce anything meaningful. So, even though an algorithm might be very easy to use, that doesn't mean that it is actually in general more useful than others. There's a trade-off. Usually the more complicated something is to implement, you can perhaps get better results under a wider variety of conditions. Not always, but these are kind of general rules of thumb. So that's really it for this first recorded lecture. I'm going to stop it here. I really wanted to just have something that focused on the general concept and really discussed all these ideas of what's going on with the annotation in plots, because you're going to be seeing a lot more of this moving forward in this module and in this class. And then the next recorded video, we'll talk about bracketing methods. Thanks for listening.